guys. Today we'll be talking about falling objects or motion under gravity, or I'm sure you've heard famously free fall. Now, back in the day, there were so many theories about how gravity works, about how the universe works, and Aristotle, having been one of the most respected scientists of the earlier centuries, had for a long time predicted or even thought that objects fall according to how heavy they are. And he had, it was the convention then, it was the understanding then that a heavier object would reach the ground faster than a lighter object. And this seems very intuitive because when you look at them, like instantly you would think, yeah, this bigger object should get to the ground faster because it's heavier, because it has more force. Force is mass and gravity. It has more force, so it should get to the ground faster. However, Galileo, who came onto the scene around 200 years after Aristotle had proposed all of these things, he came onto the scene and was challenging this idea, and he was saying that objects fall to the ground at the same rate, like they fall towards the ground at the same acceleration, meaning whether you have a small object or a big object, they're going to all fall at the same rate. And he said that whether you have a small object or big object, they'll get to the ground at the same time because they're accelerating due to gravity, and acceleration due to gravity is the same. So he did so many experiments. I'm sure you've heard of the Leaning Tower picture. This is supposed to look like a tower, with so many windows. The tower is leaning, and then Mr. Galileo is at the top here, and he did these experiments publicly. And at the time, it was almost blasphemy to go and oppose what was so known and even taught. But he went and performed these experiments, and he proved to people that falling objects accelerate at the same rate, and if you drop two objects, whether a feather and a stone, they will both hit the ground at the same time. Now, truthfully, if you ignore air resistance or air friction, then the objects fall up to the ground at the same time. But if air resistance is present, then technically there's a very, very minute difference in time at which the objects fall. This would be more noticeable if you dropped, say, an elephant and a mouse from a very, very big height. You'd be able to see the difference if that was the case. But practically or very observably, we can say that objects fall at the same rate towards the ground, and that rate is called the acceleration due to gravity, and in this course, we'll use it as 9.8 meters per second squared. So it's going to be 9.8 meters per second squared unless the question clearly specifies that use 10, because sometimes the question will say use 10, but if it doesn't, it's 9.8 meters per second squared. Whether it's positive or negative depends on what convention you are using. If you're using down as positive, it is positive. If you're using down as negative, if you're using, what am I saying? Yeah, depending on what convention you're using, as long as you stick with it, then the value has always remained the same. Well, you're going to do an experiment to verify this acceleration due to gravity. I'll give you instructions on that on Monday, and then we'll do another experiment on acceleration on Tuesday, because we're getting closer to your unit quiz and test. So let's look at an example of an object that may be falling under gravity. Or before we even go there, let's see what the equations of motion become with acceleration due to gravity involved. I hope you remember the equations of motion where x naught plus vt as the first equation, and you had v equals v naught plus at as the second equation, and then you had average displacement, the total displacement equals average velocity times time was the third. The fourth one was this change in displacement is equal to, I like to write this one like this, that displacement is equal to v naught t plus a half at squared, because initial displacement is usually 0, but technically it's supposed to be change in displacement, and if it's change in displacement, you can either write it how it looks right now, or if you don't want to write the delta and Then on the other side it would be x naught flat. I hope you know the meaning of this. And the last one was v1 squared equals v naught squared plus 2lt. Now, in these equations, what happens when we're dealing with acceleration due to gravity? The first one remains the same. These equations are true for falling objects, for free falling objects. The second one changes a little bit. Instead of acceleration, we have g. Acceleration is a vector quantity. The third one, displacement, v naught plus v1, 2, that doesn't change. The fourth one, displacement equals x naught plus v naught c plus half g c squared. Again, we're just substituting for acceleration. And the last one, v1 squared equals v naught squared plus 2gc. Let's look at an example. So you have somebody standing at the top of a cliff who throws a ball upward, then it comes back and falls downwards. So some of the interesting points along the motion of this object is this point right here, which is called maximum height. This point here, where the object comes back through its point of projection, and then at the ground here, where it's about to hit the ground. So let's say this cliff is a decent centimeters high, and let's say this guy gives it an initial velocity, and this guy can be Hudson. Let's say it gives it an initial velocity of 5 meters per second upward. As usual, I'm going to take upward as positive to be my convention. So the questions they're asking us is, one, how long does it take to get to the top? Two, you can ask, what is its time of flight? Time of flight meaning time for which it's in the air. So from this position up to when it hits the cliff. Three, you can ask, what is its velocity before it hits the ground, or the base of the cliff. When you ask for the time to get to the top, you can also ask, what is its maximum height? Or how high above the cliff does it go? So all these questions can be answered by just using the equations of motion. So remember, you first write down what you have, and then you try to see if you can use what you have to get what you don't have. For this first part of the question, we know, or we've been told, that the initial velocity equals 5 meters per second is positive. The acceleration is the acceleration due to gravity, which is 9.8 meters per second squared. And the final velocity, because it gets to this point up here, momentary rate will be 0 meters per second. So we already have three things. I bet we can use them to get time. Because if we're using the second equation of motion, which is v1 equals v naught plus, in this case, v2, then we can substitute for what we have, which is we have v1, which is 0, we have v naught, which is 5, we have acceleration, negative 9.8 times 2, and that will give me the time that it takes to get to that point. The time of flight is the time for which the object covers the displacement from here to here. Please note that I've used the word displacement. When it goes up here and it comes back here, displacement is 0. And before we get to part B, I forgot to work with this maximum height. Maximum height, in order for me to get how high above the cliff it goes, or how high even from the bottom of the cliff, I need to first compute the height up here. And I have the time, because I have got the time from here. I have its initial velocity, I have its acceleration, I have its final velocity. So which equation can I use to get that height. So that displacement, I can use x equals v naught t plus a half gt squared. X will be the displacement above the cliff. V naught is known as 5. T is your value from here, which is known half G 9.8, and again T is your value from there squared. That gives you the height above the cliff that it covers. That's not the only equation you can use. You could also have used x equals v naught plus v1 out of 2 times 2, where you have each of those unknowns. You could also have used v1 squared equals v naught squared plus 2g x, where that's the displacement. That is the velocity, those are the velocities. So you have the final velocity because it's 0, you have the initial velocity is 5, and you have the acceleration of 9.8. All of those should give you the same answer. So I want you to try them out and see if you get the same answer. Right, now I'm going to work out part 2, which is the time of flight. The time it takes the ball to travel through this displacement. So displacement is negative 20 meters. Acceleration is negative 9.8 meters per second squared. Initial velocity, I have initial velocity is 5 meters per second. It's positive. And the only thing I need is the time, delta t. So what equation am I going to use? I don't know final velocity, but I don't need it for this problem. So I can still use this equation here. Because I'm trying to find the time, I have the displacement, I have the initial velocity, and I'm trying to find time, which will be a quadratic equation in which I can substitute and find the time. So I'll have negative 20 equals v naught t, which is 5t, plus a half, I'm leaving it negative because acceleration is negative 9.8, times t squared. That is a quadratic equation which will solve for two values of t, and if there's any negative value, you discard it because time cannot be negative. Alright, so yeah, I hope this helps to prepare you. Please go ahead and do the homework questions that I've posted on Google Classroom. If there are any questions, send me a question, and then I can go through the questions, or we can do a Google call and